10,000 kicks. That's what's waiting for a star like our sun right before it dies. Not a single explosion, not one clean ending. 10,000 separate, violent shoves spread out over hundreds of thousands of years. And by the end of it, the sun won't just be dead. It'll have kicked itself somewhere else entirely. This isn't science fiction. This is a model published this year by a theoretical astrophysicist at Caltech, built on data that had been puzzling astronomers for years. And it means the star you're standing under right now is going to spend its final act punching its way through space. Here's how it starts. Billions of years from now, the sun runs low on hydrogen fuel in its core. It swells. It reddens. It becomes what astronomers call a red giant. Bloated, unstable, hundreds of times its current size, swallowing whatever planets happen to still be orbiting close enough. And on the surface of that dying giant, something chaotic begins to happen. Blobs of plasma, churning, boiling material start escaping from the surface. Not evenly, not in a smooth, symmetrical wind, the way we usually picture a star quietly losing mass. Unevenly, randomly. One side spits out more material than the other, over and over in bursts nobody can predict, driven by turbulent convection happening deep inside the bloated star. And here's the part that changes everything. Every single time that happens, the star gets pushed. Physics doesn't care whether it's a rocket engine or a dying star. For every action, there's an equal and opposite reaction. Blast mass out one side, and the star recoils in the other direction. A tiny kick, barely noticeable on its own. But it doesn't happen once. According to the model, it happens roughly 10,000 times, over hundreds of thousands of years, as the red giant slowly sheds its outer layers on its way to becoming a white dwarf. The small, dense, slowly cooling corpse left behind after a star like ours finishes dying. For comparison, modern humans have existed for a fraction of that timeline. This entire process outlasts our species several times over, one small shove at a time. 10,000 random little shoves in 10,000 different directions. You'd think that many random kicks would just cancel out. Push left, push right, push up, push down. Average it all together, and the star should barely move at all. That's the obvious assumption. It's also wrong. Mathematicians have a name for what happens here. It's called a random walk. Anyone who's ever watched someone stumble down a sidewalk, swaying step by step with no clear direction, knows the truth about random movement. It doesn't cancel out, it wanders, it drifts. Over enough steps, it ends up somewhere completely different from where it started, even though no single step was aimed anywhere in particular. That's what happens to a dying star. 10,000 chaotic kicks don't average out to nothing. They accumulate into a measurable, one-directional push, a net velocity. The star doesn't just sit there shedding mass in place. It gets shoved, slowly but permanently, off its original path through the galaxy, one stumble at a time, for hundreds of thousands of years. It's the same reason gamblers eventually go broke even when every single bet is fair. String enough random events together and the outcome stops looking random at all. It starts looking like a direction. For a dying star, that direction becomes a slow, permanent exile from wherever it used to belong. Now, here's where this stops being purely theoretical. Astronomers already had a clue that something like this was happening, and for years, they didn't know why. Researchers studying binary star systems noticed something strange in the data. Wide, loosely bound pairs of stars, orbiting each other from a safe distance, kept disappearing once one of the two stars finished its life and became a white dwarf. The wide binaries were quietly vanishing, system after system, with no obvious explanation. Think about what that means. Two stars, bound together by gravity for billions of years, traveling through the galaxy as a pair the entire time, born together, aging together. Then one of them dies, and the partnership just breaks, not because of some catastrophic collision, not because of an external force ripping them apart, because the dying star kicked itself hard enough to escape its own partner's gravity, all on its own. If the kick speed is faster than the orbital speed holding the binary together, the math is simple, almost brutally so. The bond snaps. The two stars, companions for an unimaginable stretch of time, go their separate ways forever, drifting into the galaxy with no path back to each other. And the wider the orbit, the weaker that bond already was to begin with. Some of these binary pairs are separated by distances so vast that gravity barely holds them together at all. A whisper of a connection stretched across trillions of kilometers. It doesn't take much of a push to break something that fragile. A single kilometer per second, applied at just the wrong moment, is more than enough. According to the researchers' estimates, that net kick lands somewhere around 1 kilometer per second. That might not sound dramatic, but out here, where the gravity holding two stars together can be almost impossibly weak across such vast distances, it's more than enough to unravel a relationship that's lasted longer than complex life has existed on Earth. To be clear, this is a model, not yet a direct observation of the mechanism caught in the act. It was presented this year at a major astronomy conference and is currently under review for publication. The underlying evidence is solid. The wide binaries genuinely are disappearing, confirmed across multiple surveys, but the precise mechanism explaining why is still being tested, and scientists are already designing ways to search for a direct proof. Stick with me though, because the model doesn't stop at quietly drifting apart. It gets more violent than that. If a dying red giant happens to be locked in a tighter orbit with a companion star, close enough that a random kick could send it lurching in the wrong direction instead of drifting harmlessly away, the researchers propose something far more dramatic could happen. Instead of slowly separating, the kick star could get shoved directly into its companion. A collision. Between two stars, one of them already in its death throes, at speeds and energies almost impossible to picture from the ground here on Earth. If that scenario plays out the way the model predicts, it wouldn't be a quiet ending. It would be one of the most violent events a star system could ever produce. And it would be entirely self-inflicted, caused by nothing more than the star's own chaotic, dying breath, with no outside villain to blame. Picture it for a second. Two stars that have shared an orbit for billions of years suddenly slammed together because one of them couldn't stop twitching on its way out. Not a war between two systems, not an outside intruder crashing the party, just one dying star, stumbling sideways at exactly the wrong moment into the one companion it had left. Astronomers don't have direct proof this precise scenario has happened yet, but they now know what signature to look for in the data. A specific pattern in the debris, in the leftover light, in the chemistry of the wreckage. And if they find it, it would confirm that some of the universe's most violent stellar explosions aren't triggered by outside forces at all. Not by a passing black hole, not by some cosmic collision from elsewhere. They're triggered by a star kicking itself to death. Now think about what this means for every star system built like ours. Stars are almost never born alone. They form in dense clusters, in pairs, sometimes in tight orbits that last for the entire lifetime of both stars involved. Companionship, in stellar terms, is the default state of things. Most stars have some kind of gravitational partner somewhere for most of their existence. A sibling from the same nursery, a companion locked in orbit, a cluster of relatives scattered nearby, all born from the same collapsing cloud of gas. And, according to this model, the very last act of a star's life, the process that finally kills it, might also be the thing that severs every one of those bonds. Not an outside threat, not a passing black hole, not some dramatic cosmic accident. The star's own death throes, quietly kicking it loose from everything it's ever been connected to, one random shove at a time. Which brings us back to where we started, because our sun is exactly this kind of star. Billions of years from now, the sun will swell into a red giant, just as described. It will begin shedding its outer layers in that same chaotic, uneven way. It will experience its own version of those 10,000 kicks, its own random walk through space, its own slow drift away from wherever it happens to be at that point, in its long orbit around the galaxy. Every planet still orbiting nearby at that point, whatever's left of them, will feel the consequences of a star that can no longer hold a steady course. By then, humanity will be long gone, one way or another, and whatever remains of the solar system will be reshaped by that same violent, stumbling process. The sun that's held everything in this system together for billions of years, that every planet has orbited faithfully since the beginning, will spend its final chapter kicking itself apart from anything still close enough to feel it. No comet will be there to record it. No planet will still be intact to watch it happen. Just an old, dying star, alone in the dark, taking 10,000 small, stumbling steps away from everything it ever held on to. So here's the question worth sitting with. If the very thing that finally kills a star is also the thing that pushes it away from everyone it's ever been connected to, is there any such thing as dying peacefully out here at all? Or is every star eventually kicked out alone